What do you think is the probability of obtaining exactly 5 heads and exactly 5 tails in 10 flips of a fair coin? The most common intuition here is to say that the probability is 1/2. It turns out to be much less than 1/2, only about 0.25, and we'll see later on why this is true and why it makes sense. We'll continue working with the experiment of flipping 10 coins and counting the number of heads and tails. We'll do this to work up to a concrete understanding of what we specifically mean by the word probability. Now that word, experiment, is one that we'll be using quite a bit in this course. We can repeat an experiment many times, but a single run of this experiment will be to flip a coin 10 times. Now you can either flip an actual coin or use the very useful online coin flipper at www.random.org/coins. Let's see what happens when we go there. I can select here on this drop-down menu the number of coins. I can select as many as 200, but for the moment let's stick with 10. And I can select a type of coin. Just for the sake of familiarity, let's pick an American penny, and we click here to flip. Lo and behold, we happen to have gotten 5 heads and 5 tails. Okay, that's great. But I can keep flipping again, and oh, look, I got 8 heads. Flip again, I got 5. Flip again, 3. Flip again, 5. I flip again. I flip again. 5. I flip again. 6 heads. I flip again. 7 heads. This is quite hypnotic or addictive. This is like drugs for mathematicians. So let's flip one more time, and whatever I get on the next flip, I'm going to record that as my actual data. Alright, I obtained 4 heads and 6 tails. 4 heads, so 4 heads out of 10 is 0.4. Okay, the fraction of flips which are heads expressed in decimal form is 0.4. 40% of our flips so far have been heads. Now, we can repeat this experiment. We can keep doing this. Our first data point was 4. But as we repeat, we can keep track of something else which is important, and that is the overall fraction of all the flips we've done so far which have turned out to be heads. Here's what I mean by that. I flip again, and this time I obtain 5 heads out of 10. My second run of the experiment produces 5 heads. Thus far, total, I have 9 heads out of 20 flips, and when I compute, that's 0.45. 45% of the flips thus far are heads. I do it again. I obtain, again, 5 out of 10. So the running tally is I now have 14 out of 30. And that is approximately equal to 0.4667. So my overall fraction of flips, which are heads, is slowly increasing here. So let's do this a few more times to appreciate the pattern that emerges. Now we have 4 once again. My running tally is now 18 out of 40. 0.45. Okay. Let's flip again. I again obtain 4 heads. So my tally is now 22 out of 50. That's 0.44. Flip again. Let's flip again, see what happens. Now I've got 5. No. Now I've got 6. For a total of 28 out of 60 thus far. We're back to 0.4667. Another flip. We'll do this 2 more times and see what happens. Oh, now we've got 7. That's a total of 35 out of 70. And wouldn't you know it, we've exactly hit 0.5 thus far. Last flip. And now we've gotten 3 heads on our last performance of the experiment for 38 out of 80. And we'll stop there That equals 0.475. Okay, what just happened? With each act of performing the experiment once, each successive act of performing the experiment once, each act of flipping 10 coins, we acquire more data. As we keep updating in this column, as we keep updating our running tally, as we keep recomputing the fraction of total flips thus far, which have come up heads, we find that this fraction, expressed as a decimal here to make the comparisons easier, this fraction fluctuates. Moreover, it doesn't keep moving in the same direction, right? So the jump from the first number, 0.4, to the next number, 0.45, is the largest of all the jumps. There are smaller jumps after that, but they aren't all smaller, right? This is a substantial jump here from 0.4667 to 0.50, right? So the jumps don't necessarily get smaller, and although it seems that we're working our way closer and closer to 0.5, first of all, notice that although the numbers, these fractions seem to be getting closer to 0.5, then they start getting farther away before they start getting closer again. Furthermore, having reached 0.5, having acquired data in which half the flips, exactly half, are heads, with the next performance of the experiment, oh, now we're thrown off again, and it's no longer exactly 0.5. The most important point is that although this fraction fluctuates, especially at the beginning, as we keep repeating the experiment and tallying the overall results, the fraction tends eventually to stabilize near 0.5. If we kept going, it might veer away from 0.5 a bit longer, but the idea is that eventually it will get closer and closer to 0.5. Another important point here is that as this fraction changes, it can actually veer away from 0.5, as we see in this last step here, just as surely as it can get closer to 0.5. So that it's not obligated to get literally closer and closer to 0.5 at every step. In the long run, it gets closer to 0.5 in some sense. Is it exactly half the number of flips which show heads and the other half tails? No, certainly not exactly. Not even after 80 flips. In the short run, anything can happen. In the long run, what tends to happen is not that the fraction of heads reaches exactly 0.5 necessarily, but rather it stabilizes somewhere close to 0.5. To put all of this together, the behavior of the coin is random, but not chaotic. What does that mean? It means that on any one particular flip, there's no way to predict whether it will show heads or tails. Similarly, if you flip a small number of times, there is still a great deal of variability. In the long run, the fraction of flips resulting in heads will tend to stabilize at or near 1/2, which means that there is much less uncertainty about what happens in the long run than there is about what happens on each individual flip. In the long run, as we keep repeating the experiment and computing this overall fraction of heads which have appeared, there is one number which this fraction of heads gets closer and closer to. And that's what we mean by the probability of obtaining heads on a single flip. If we kept doing this long enough, eventually these numbers would get very close to 0.5. The probability, bottom line, the probability of obtaining heads on a single flip equals the fraction of flips that we would obtain as heads in the long run if we kept repeating the experiment. This is all about the long run. To understand what probability statements mean, we have to think about repeating an experiment and looking at what happens in the long run. Now you get to experience all this yourself. Before going on to the next video, use the online random coin flipper to perform the experiment of flipping 10 coins at a time and to carry out 8 performances of this experiment, exactly as we've just done in the video. So do exactly as we've done earlier by computing a running tally at each stage of the overall fraction, written in decimal form, of flips which are heads. It's important to write this in decimal form in order to be able to make an easy comparison between successive numbers. It's important to keep track of your results. This will be one of your homework problems. Also, comment on whether the numbers that you obtain here as these fractions are getting consistently closer to 0.5 or whether they sometimes veer away from 0.5.